Welcome everybody to the 10th and last lecture of Informatik 1. Today I will give you a brief introduction into machine learning, which is also known as artificial intelligence.
So what is machine learning, or in short AI? So if we look at the definition by author Samuel, then machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. And if we look at a more recent definition by Tom Mitchell, then a computer program is said to learn from experience E with respect to some task T and some performance measure B if its performance on T as measured by B improves with experience E. So this might seem a little bit long and complex, but we will see what this means soon, a few slides later. So AI is basically the science of making machines smart. If we look at Gmail, for example, Gmail has an inbuilt spam detection system, which is based on artificial intelligence or machine learning. And every time when we mark an email as spam, then the algorithm, the AI in the background, improves and learns to better separate spam emails from normal emails. So if we look at the example using Mitchell's definition of the previous slide, we can say that the task is classifying emails as spam or not spam. So this is the task of the program, to classify emails as spam or not spam. And watching you labeling the emails as spam or not spam is the experience of the program or the experience of the AI. So the more you label the emails, the correct emails as not spam and the spam emails as spam, the more you label, the greater gets its experience. So this is the experience. And the performance measure is the fraction of emails which got correctly classified as spam and those who got correctly classified as not being spam. So this is the performance measure. So we have a task, experience, and the performance measure. And if we look at the machine learning algorithms which are out there, we can basically identify three main areas. The first being the supervised learning algorithms. So the idea behind supervised learning algorithms is that we teach the computer what to do. So an example would be the spam or not spam classification, what we already learned about. So we teach the computer how spam emails look and how normal emails look. So we explicitly say it, this is spam and this is not spam. Then another field is called the unsupervised learning. And the idea behind that field is that the computer finds itself a hidden pattern on its own. So we don't say these are spam emails and those are not spam emails. Instead, the computer on his own finds that there are two sorts of emails in our data set and that they both look different. And then from that we can deeper investigate those two patterns of emails basically. And the last field is called reinforcement learning. And the idea behind reinforcement learning is that it's inspired by the brain. So it's inspired by how humans learn through a reward signal, or as we have it in our human brains, a dopamine system. So each time we do something right, we get a dopamine kick in our brain, which is a reward signal. And so we know, okay, this was good, and therefore we should keep doing that. And yeah, if we do something bad or wrong, then we don't get this reward signal, and therefore this behavior is not reinforced. So each behavior which is correct gets a reward and therefore is reinforced by our brain or by the AI algorithm. So those are the three main main areas or main classes of AI algorithms or machine learning algorithms. So let's look at the first family of learning algorithms, namely the supervised learning algorithms. Here we have the regression as an example. So regression is a supervised learning algorithm, and the data what we're using in this example here is called the house pricing data set. So yeah, it contains the prices of some houses, and it also has some additional features which describe a house, for example, the size in square meters and so on, and the price. And as you can see here in this plot, the larger the size in square meters, the larger is also the price. So you see here we have a positive correlation basically. So the higher the size, the higher also the price. And what a regression does is it tries to lay down a line, so it's a straight line through the data, and the goal of the regression is to minimize the error between the line and the data, so to minimize the distance between the actual data and the line which was fitted. So if we look, for example, at the size in square meters, so if we have, for example, a house with 600 square meters, then if we draw a vertical line and if we build the intersection with our fitted straight line, we can see that we can predict a price of 900 euros, for example. And the goal is to build a prediction model. So we learn from data. So we learn from a few house prices which we got. So we got a few houses where we know the size in square meters and also the price. And then using this data, we try to learn a model, which is in this case just a straight line. And we want to fit this straight line onto this data, and we want to minimize the error between our prediction and the actual data. So this is the goal. And then once we have the model, which is in this case the straight line, which was fitted onto the data, we can then use this model, this straight line, to predict new house prices. So when your friend then comes to you and he says, okay, I have a house which has 600 square meters, and he asks you how much for how much money can I sell it, then you can just throw the data into your model, and then you can predict a good price, which is in this case, for example, for 600 square meters, 900 euros. And another possibility would be to not to fit a better model. So in the step before, we fitted a straight line, but here you can see we fitted a curve, and now you can see that it fits the data better. So we get a smaller error between our line and the actual data. And now if we look at the same size, again at 600 square meters, you can see that the model now predicts a higher price. So we can now sell our house for not 900 euros as previously, but now for 1,000 euros. So, which is better for us because we earn more money each month. So the better the model, the better the prediction. All right. So in supervised learning, the right answers are already given. So we have a data set where we already know the right answers. And in case of the house pricing data set, we already know the price of the houses. So we know the right answers and we want to learn from these right answers. And there are two types of supervised learning algorithms. First being the regression, which was the example what we currently looked at with the house prices. So we want to predict a continuous valued output, like the price, for example. And another type is the classification. So we want to predict a discrete valued output. So a simple binary variable. So yes or no. So for example, does the patient have cancer? Yes or no. And talking of cancer, there's also a very famous data set out there called the breast cancer data set. So again, if we look at the data, you can see here at the x-axis we have the tumor size in square millimeters, and on the y-axis we have a binary value stating if the tumor is malignant, yes or no. So we have a binary output there. And to Deutsch, malignant means bösartig and benign means gutartig. Alright, so we can then, so given that data, we can make already an intuitive prediction. So imagine that a patient comes to you and wants to know if his tumor is benign or malignant. So, and the patient's tumor size in square millimeters is, for example, 15 square millimeters. So as shown here at the green with the green arrow on the x-axis. So if you look at this data here, you can see, for example, if the tumor size is 15 square millimeters, then we have only one case, the red cross at the upper side, which is 10 millimeters and is malignant. And we have 4 cases where the tumor size is smaller than 15 square millimeters and it is benign. So, and we only have 2 cases. If we look at the lower part, we have only 2 cases which are benign and are greater than 15 square millimeters. And we have 1, 2, 3, 4, 5 cases which are greater than 15 and are malignant. So just by looking at the data, we would probably say that the tumor size with 15 square millimeters is probably benign. And we can simplify this notation here by reducing it to one axis and introduce different marker symbols for the different values being malignant or benign. So we can just bring down the benign cases as shown here using the orange crosses, and the red crosses, which are malignant cases, we just replace the marker symbols, for example, with circles. So we have simplified the notation into one. So we reduce the number of axes from 2 axes to 1 axis and just encoded the information with different symbols. So we have the same information but reduced the number of axes which we needed to visualize the data. And now we can introduce a new feature, a new dimension. For example, we can introduce the age. So we now look the age of the patient and the tumor size. And again, we can visualize some data. So we have some young patients there with a small tumor size, and those cases were benign. So those were gutartig. And then we can just draw a few more cases, a few more, and then again a few more. And you also see the older the patients get, the larger also the tumor size gets slightly. And then we can draw a few malignant cases, bösartige Fälle. And here you can see the age is way higher, and also the tumor size is a little bit higher. And then we can draw just a few more examples here. And as you can see here, here at those malignant cases, the tumor size is very large. And yeah, the age is also a little bit higher. But we also have a case, for example, where the patient is, for example, 30 years old, and yeah, the tumor size is 40, around roughly 40 square millimeters. And now the goal of a classification algorithm in supervised learning is to separate those two target values, or to separate the malignant cases from the benign cases in a way in a way that we can reduce false predictions. So we want to find a separation of the data where we can perfectly separate the data. So we need to find a separation line. So we can just draw two more cases here so that the task gets a little bit harder. And for example, if we then want to predict a new example, as indicated by the green circle here. So for example, again, a patient comes to you and wants to know if his or her tumor size, which is, let's say, 12 square millimeters, and the patient is about 23 years old, he or she wants to know if the tumor is benign or malignant. And given that data here, you can draw a straight line into the data, which tries to separate a malignant from benign cases in the best possible way, which means you want to reduce false predictions. So what you want here is that all the data values, all the cases which are on the left side, in this case from the straight line, you want that all those are benign cases, and all the values or all the samples which are on the right hand side of the line are malignant cases. But as you can see here, we couldn't perfectly separate the data because in this case here, two cases are still benign and two cases are still malignant on the left hand side. So we weren't able to perfectly separate the data. However, we did a pretty good job, and if we would have learned this straight line as a classification model, then we would see that the green point is on the left hand side of this straight line, and therefore we would classify the new sample, the green one, as being benign, since it is on the left hand side of our separation line. So if we look at the number of features what we can use, or dimensions what we can use in order to make a prediction, we can use, for example, the perimeter of a tumor, or the thickness of a tumor, the symmetry of a tumor, and the compactness of a tumor, and so on. So we can use a lot of features there. However, it gets really, really difficult to visualize all this data, because we can only, as a human, we can only process data visually with 2 or maximum 3 axes. So we can't really visualize 4-dimensional data. So it's not that easy, right? So yeah, we can have a lot of features which we use. However, as a human, it gets then really, really hard to process all that information. And therefore we need smart algorithms, machine learning algorithms, artificial intelligence, which analyzes all this data, which consists of a ton of dimensions, and tries to extract patterns out of it, which fits our goal, which was in this case to classify a tumor being malignant or benign.
All right, let's look at an example. Here I have prepared a notebook where we will build a simple machine learning model on breast cancer data. And this whole notebook is based on this article here, which I have linked. And yeah, we all know breast cancer. And yeah, breast cancer is one of the most common cancers among women worldwide. And yeah, those correctly diagnosing breast cancer and classification of patients into malignant or benign groups is the subject of much research. And basically what this means is a tumor can be either malignant, zu Deutsch bösartig, or benign, which means gutartig. And therefore, if we measure some properties of a tumor, for example, the size, the density, and so on, we can then use this information in order to predict or classify if this tumor is malignant or benign. Alright, and to do so, we can use scikit-learn, which is a Python library. If you remember the data analysis pipeline, we are now at the last step, namely the action step, where we can really learn specific models for our data, which we can then use to predict new things. And in this very particular case, given the data, what we have, we want to predict if the tumor is malignant or benign. To do so, we use the scikit-learn package, which contains a lot of statistical models which we can use. So here in this cell, I import from sklearn .datasets the breast cancer datasets. And as already said, sklearn contains many machine learning algorithms and also datasets which we can use. As always, I import my matplotlib, pandas, and numpy. So we execute this cell here, and then in the next cell I just load the dataset and convert it into a data frame object. We just use the function what we imported over here, and we then do some pandas magic, so to say, and build out the data frame. And I also include the target variable in our data frame. So the target variable shows me whether the sample, the tumor sample, is malignant or benign. So this is the target variable. So this is the variable what we want to predict or to classify. And also additionally, since the target label is a binary label, which means it's either 0 or 1, we also include the second column, which includes the target names. So this is really then the string if it's benign or malignant. So we execute this, and I can just print out, for example, the target names which are in the original data. And you can see we have two target names, namely malignant or benign. This is a list, and we can also print out the target itself. Target, and you see this is a huge list of zeros and ones. 0 meaning it's malignant, and 1 meaning it's benign. Alright, so here you see we have a binary vector which contains only zeros and ones, and here the target names is then a column which contains the actual targets as labels, as strings. So if we just print the first few rows of our data set, of our data frame, you can see here at the beginning we have all the features or all the dimensions or measures which describe the tumor. For example, the mean radius of the tumor, the mean texture, the mean perimeter, smoothness, compactness, and so on. We have a lot of metrics here which we can use for our prediction. And then at the end you can see our two columns, namely target, which is the binary classification, whether it's malignant or benign, and here the last column contains the string label. So 0 meaning it's malignant, this tumor, and yeah, 1 meaning it's benign. All right, so we have already looked at the target names. Then we can also print out the shape of our data frame to see how many samples we have in our data set. And we can also calculate the fraction of benign tumors, what we have in our data set. So each measurement here, so each row in our data set comprises one patient or one sample, and one sample can either be malignant or benign. And yeah, with this line here, we calculate the mean number of benign tumors. Since you see here, 0 is meaning malignant, and therefore 1 means benign. And if we calculate the mean over this binary column, we get the fraction of benign tumors. So let's execute this. So we see we have roughly 569 rows in our data, which means we have this number of samples in our data, and we have 32 columns. And if you remember, the last 2 columns represented our target variable, what we want to predict. And therefore we have 30 columns left, which we can use to classify for our prediction. So with the 30 columns, we want to build a model which we then can use to predict whether the tumor is malignant or benign. And we see that about 62% of all the tumors in our dataset are benign, which means gutartig. Then here, one of the first things what you always do in data analysis, or if you build a model, is to plot the distribution of a few columns, of a few metrics. So the first thing what we can do is also visualize the distribution of malignant and benign samples. So we basically visualize this ratio here. To do so, we use a histogram and give it the target names as data. And yeah, let's look. As you can see here, we have about 350 benign tumors in our data set and about 210 malignant tumors in our data set. So 63% roughly are benign and the rest is malignant. So we can then move on and plot the distribution of multiple columns or features in one plot. And in this case, all the plots share the x-axis. Here you can see I create the plot with 2 rows and 2 columns. So in total we have 4 figures or four plots with 1 figure and 4 plots in it. Yeah, and you can see here in the first I plot the mean perimeter, then in the second the worst perimeter, then yeah, those 2 variables. And again I use histograms in order to visualize the distribution of the column. So the distribution gives me a hint or feeling how the values in this particular column are distributed. So let's see how it looks. And you see here the 4 plots, and you see those 2 plots share the x-axis here. So here we have 50, 100, 150 and so on, and here we have 0.05, 0.1 and so on. And as you can see here, regarding the just let's look at this plot, the worst perimeter, most of the samples have a worst perimeter of, let's say, what is this, 80 maybe, and also the second most occurring value is about 100. So yeah, this is the typical worst perimeter. So here we have the most values. More particular, we have about 140 samples which have a perimeter of about 80. This is what the distribution tells you. All right, so then we need to split up our data set. So why do we need to split up our data set? So we always need one set of training examples, which was one set of examples which we use to train the model. Therefore, it is called the training set. So we use this data to train the model. And then we use another set of examples which we use to evaluate our model. So we use one set to train our model and one set to evaluate our model. And it is really important to have a distinct set of values since we want to evaluate our model on new unseen data, right? So because if we evaluate our model on the data which we used for training, we can just use a simple database where we store all training values, and in this way we could achieve perfect classification. So this makes no sense. So we always need two distinct sets, one for training and one for testing or evaluation. And we can do this again with scikit-learn. So scikit-learn has an inbuilt functionality for that. It's called train test split, and it splits up our data set into distinct sets. So here we have slight mathematical notation. So x, the matrix x holds the training data and all the features, and y always holds the target labels. So this is the data which we use to predict the target. So with x we want to predict y, and so we have since we need two sets, a training set and a test set, we have x train, which contains the 30 features here in order to predict the target. So it begins with mean radius and it goes to worst fractal dimensions, and y contains the target label. So this is the label what we want to predict at 0 or 1. 0 meaning malignant and 1 meaning the tumor is benign. So we make this train test split, we pass it our input data being the metrics or values which describe the tumor, and also our target variable what we want to predict being the target, and we can pass it a test size, which means how large should our test set be, and we say our test set should be 25%, so 25% should be reserved for our test set. Yeah, that's basically it. And if we execute this, we can again look at the xtrain variable, and as you can see, now we have only 30 columns left. This is because x only contains the features what we want in order to predict the target label. So this contains all the features without the target labels, and since we had two columns which hold the target labels up here, as you can see here, we have two columns which are target. Therefore, we neglect those two in our x variable, and therefore we have only 30 in our x, and not 32, right? So we have 30 columns here. And our y variable only contains the target values. So this is simply a vector, which again holds the target, which we want to predict. So being either 1 or 0. 1 meaning the tumor is benign, and 0 meaning the tumor is malignant. We can then print out the shape of the training and the test set. As you can see here, we have now about 426 samples for training, and we have reserved 143 samples for testing. So this is 25%. And if we sum up those two numbers, we get the whole data set. All right, and you can see here the shape of y is only we after the comma we have no value because it's one dimensional. We only have an array. All right, so what we can now do is, since we want to make a model which predicts if a tumor is malignant or benign, we could think that the distribution for malignant tumors is different than the distribution for benign tumors. And we can check this for a single feature, for example. So let's take a look at the distribution of the mean perimeter, and we plot the histogram for malignant tumors. So we plot the distribution for all the tumors who were malignant, and we plot the mean parameter of it. We also plot the mean parameter of all the benign tumors, and we give it a different color. And yeah, we then just compare the two distributions, and we do the same for the mean concave points. So let's see. Here you can see the orange histogram shows the distribution of the mean perimeter for benign tumors, and the blue histogram shows the distribution of malignant tumors of the feature mean parameter. So you see here that benign tumors have in general a smaller mean perimeter than malignant tumors, right? And similar you see here if we look at the feature or at the dimension mean concave points. You see again that benign tumors in orange here, the distribution of the benign tumors is again smaller than the distribution of malignant tumors. And just by looking at those two plots here, one could already come up with a very, very simple model which we could use in order to classify if a tumor is malignant or benign. And to give you a little bit more a hint, we can plot two vertical lines in there using AXV line at the values 90 and 0.045. So let's see. So we just plotted a vertical line here, and a simple model could just take those values here. So for example, the value 90. So, and all tumors with a mean perimeter of smaller than 90, for example, we could classify as benign, and all tumors with a mean perimeter of greater than 90, as you can see here, we could classify those as malignant, for example. So we have one simple if-else statement which we can use in order to predict if a tumor is malignant or benign. So this is a very, very simple model, and we built basically this model by just looking at the data what we visualized. And we can only come up with such a simple model if we do this data visualization, and using this data visualization we can extract out information of the data and come up with such a simple model on our own. However, this would be just one simple if-else statement, right? And you see here we have here another feature, mean concave points. We can do the same here. So for example, if mean concave points is smaller than 0.045, we can classify the tumor as benign, and if it's greater than 0.045, we could classify it as malignant. All right, so but we have then two if-else rules, but we don't know how we should connect them, right? Which one should we check first? What if mean perimeter is smaller than 90, but the mean concave points is greater than 0.045? What do we do then? So if we increase the number of features what we want to include in our model, it gets more difficult. So we need to come up with a more sophisticated model here. But let's look at how our simple model would perform. So we just create this simple if-else rule on mean concave points, for example. So let's see the values of mean concave points. So you see it's in the magnitude of 0.0 something. So we can then create just a simple function called simple cancer classifier, which takes our cancer data, and if mean concave points is smaller or equal to 0.045, then we classify it as benign, and otherwise, if it's greater, we classify it as malignant. So as already said, if the value is in this area, we classify it as benign, and if the value is in this area, we classify it as malignant. So yeah, let's define this simple classifier, and let's call it on our test data. So you see we pass it our test data here, and let's see what the prediction looks like. So you can see here the target values, what we predicted, either 0 or 1, using this simple if statement here in a list comprehension. And we can also print out the true labels for our testing data. So this is the actual true data. These are the right answers. Therefore, we have a supervised learning algorithm, right? So this is the true labels, and this are our predicted labels. So this is what is actually true, and this is what our model predicted. And now we want to calculate the fraction of correct predictions of our simple if-else rules. And this is called the accuracy score. So we want to calculate the accuracy of our model. And again, scikit-learn has built-in functionality for that. And yeah, we can make predictions on the training data. We can make predictions on our test data. And then we print out the accuracy score for both our training data and our test data. And you see that if we apply our model on our training data, we get an accuracy score of 90%, which means in 90% of the cases, this simple if-else rule made correct predictions. And on the testing data, so we learned our model by looking at the training data. And if we apply our model on unseen test data, it is in most cases slightly worse. However, the model still achieved an accuracy of 86%, which means in 86% of the cases, our model made the correct prediction, which is quite good for just a simple if-else rule, right? So however, we have some advanced statistical models in scikit-learn, for example, a decision tree. This is called the decision tree classifier. We can import it. Just don't go into the details there. I define this statistical model, this machine learning model, the decision tree. Then I call the fit method using the training data. So I fit the model on the training data. I do this here. And then I can visualize basically the model, which we just learned. With this data, and we get a nice tree here, and this tree is basically just a collection of simple if-else rules, and the node here at the top represents the most important feature or the most informative feature which could be used for the classification. So this is the feature which contains the most information for our prediction. And as you can see here, the top feature is mean concave points. And it says, okay, if the mean concave points is smaller or equal to 0.049, then let's go to this area here. And as you can see here, in this case, the tumor is in most cases benign. And if mean concave points is greater than this value, we go this bar down there. And in this case, the tumor is malignant. And you can see here, you can just apply some further rules. For example, if the mean concave points is larger than this value, we go up here, we go down here, and if worst area is smaller than 785, we go this, and then the tumor is benign, and in all other cases the tumor is malignant. So this is basically a tree of if-else rules, right? and we learned, or the model automatically learned this tree of if-else rules on its own by just looking at the data and the right answers which we gave the model. So by just giving the model X train and Y train, we learned this decision tree here. And let's see how this new classifier now scores. So let's look at the accuracy score. And now you can see we got the slightly higher accuracy score, namely we got 93% on the training set and 91% on the test set. So yeah, in 91% of the cases our decision tree made the correct prediction. And if you think this is not a big difference between our simple if-else classifier, yeah, as you can see here, for our simple if-else classifier, we already used the topmost feature, which contains the most information for our prediction. So in order to come up with this if-else rule, I cheated a little bit and first built this decision tree and looked what feature is the best one in order to make a prediction, and I then just used this feature for our if-else rule. So yeah, I cheated a little bit there, but yeah, I think you get the meaning behind this. So by just using a simple if-else rule, you can already make a good classifier. However, yeah, this is just a very simple model, and the more sophisticated model is just a decision tree. Yeah. So at the end, I would like to show you also a neural network. So for those of you who already heard some things about neural networks, we can also train neural networks in Python with a few lines of code. And for those of you who do not know neural networks, a neural network is basically an artificial neuron which is inspired by the neuron which humans have in their brains. So it's basically a human-inspired learning model. And yeah, what I will show you here is that with a few lines of Python code, you can already train a neural network, which is very powerful. Yeah, I don't go into the details there. Here I just built a neural network with 2 layers, and yeah, again, fit it on our training data. So let's see. And again, then here I use this neural network to predict target values on our training data and on our test data. And then at the end, I just again print out the accuracy score for our training and test data. So let's see. And now you see we get a very good performance, or very good or very high accuracy. And you see with a neural network, in 98% of the cases on the training set, we predicted the correct result. And in 97% of the cases in the test set, we made the correct prediction. So using this neural network, we were able to predict in 97% of the cases if a tumor was benign or malignant. But just using, yeah, what is it, 1, 2, 3, 4, 5, with 5 lines of Python code, we trained a neural network which could predict correctly in 97% of the cases if a given tumor was malignant or benign. I think this is a very great result with just a few lines of Python code. All right, so I hope I was able to give you a nice glimpse on machine learning and machine learning models, which we can use in Python. So yeah, this is just a glimpse for the future. So yeah, I hope I was able to motivate you a little bit to get a little bit deeper into this topic of machine learning. In supervised learning, we got to know the right answers. So we know if a tumor is, for example, malignant or benign. So we have a few dimensions describing
the tumor, and we got the right answer. So we know, is it malignant or benign? Or if we look at the spam example from the beginning, we have, for example, the email text and the corresponding label, if it is spam or not. So we know already the right answers and we can learn from the right answers. On the other hand, in unsupervised learning, we only have the raw data without any labels. And can you find some structure in it? And if yes, then you basically have applied unsupervised learning. And what you did is you extracted patterns out of the data. And here, as you can see, we can identify two clusters. So here on the left-hand side, we have, for example, cluster A, and on the right-hand side, we have cluster B. And yeah, so we don't know the right answers. Therefore, the algorithm needs to find patterns on its own. So to recap, in unsupervised learning, we don't have any labels available which describe our data. Further, we want to detect groups or hidden structures in the data. And this is also known as clustering. And the goal of clustering is to minimize the differences within a group. So all the samples inside of a group or inside of a cluster should be minimized. So all the differences in a group should be minimized. So they should be as similar as possible. And the differences between those detected groups or clusters should be maximized. So to get a real-world example how clustering is used in actual science, I would show you this video if we would be in the lecture hall. But since we are not in the lecture hall, I will put the link of this video in the video description of YouTube, and I will also put it again into the Teach Center. So a short summary of the video. What those four scientists basically did was they collected a bunch of survey data. So yeah, they interviewed a lot of people, or they made a test online where they basically asked all the questions about the Big Five. So for those of you who are already familiar with the Big Five, this is a concept in psychology in order to determine the personality traits of people. So there are 5 personality traits, and yeah, you can ask specific questions to determine each personality trait, or which personality trait each person has. And they did basically that. So they asked them all the questions about their personality traits, and then they had a ton of data consisting of 5 dimensions basically of those Big Five, and they then applied clustering on the data and found out that there are 4 big clusters, so that there are basically 4 personality types which occur. And yeah, as always, I would encourage you to watch this video. This is a really nice video, and in my opinion, this is a really great finding which was done with simple clustering algorithms. So the last family or machine learning algorithms family what we will talk about is the reinforcement learning algorithms. So imagine that we have an AI system which is in an environment, and such an environment can be the real world or a virtual world, for example. And then the system tries to achieve a goal in that environment. So for example, the system wants to earn money, or the system wants to save power, or the system wants to score points. And then the system interacts with the environment in 2 ways. So the first one is it gets observations about the environment. So for example, using sensory systems like cameras and so on. And those observations are normally very noisy and incomplete. And then the job of the system is to build a best statistical model of the world or of the environment. And then the second job of the system is to pick the best action that will get its closest to its goal. And this then again, this action of the system will again change the environment and lead to new observations. And this diagram here has lots of hidden complexity in it. And if we solve this diagram, we basically solve intelligence. And because this is the way all humans and mammals learn, through the so-called dopamine system, this is a very, very complex and difficult task. And a company who is trying to solve this diagram is called DeepMind. And yeah, the goal of DeepMind is to solve basically intelligence. And therefore, they started with a virtual environment. And in this case, they took the Atari game framework. So for those of you who know Atari, it's basically like a Game Boy, but older. And yeah, there are tons of Atari games out there. One famous game is called Breakout, which you will see in this video here. And again, here you have an environment, which is the Atari game, and they implemented an agent or a system using AI algorithms, which observed the screen. So it just looked at the video screen. So it just really looked at the pixels itself, and the reward signal were the scored points. So it has the observations in forms of the pixels. The reward signal, like the dopamine system, was the score. So the high score or the score which it is achieved. And the actions which it took with the environment was the slider at the bottom. And the goal was to achieve as many points as possible by picking the best actions. And they implemented a very, very good system using very, very complex algorithms, namely a neural network. And the network was called DeepQ network. And just have a look at this video. It's a really, really nice finding. And their findings were actually also published in the Nature journal. And Nature is basically the best scientific journal out there. So if you publish a paper in Nature, this is the golden standard. So there's nothing better which you can do. And they achieved this multiple times. So please have a look at this video. And again, I will put the link in the video description and YouTube, and also in the Teach Center. So obviously DeepMind did not stop after implementing their DQN network. So after they basically have mastered all the Atari games to a superhuman level, they thought to tackle a very prominent Chinese game, namely Go. And for those of you who do not know Go is a very similar game to chess. However, it's probably one of the most complex games out there in the term of the number of possible games or moves you can make. And however, the game itself is pretty simple, so there are pretty simple rules. And just to give you some numbers, how many possible games there are in Go. The universe has 10 to the power of 80 atoms in the observable universe. So 10 to the power of 80 atoms. And the game of Go has 10 to the power of 700 number of possible games which you can play. And so this is really huge. So experts said that it wouldn't be possible to beat a human Go player within the next 10 years by a computer. So it wouldn't be possible to implement a system, a computer program, an AI, which is able to defeat a professional Chinese Go player. And yeah, DeepMind thought, okay, we take the challenge, and yeah, implemented a system called AlphaZero or AlphaGo, which learned to play Go. And yeah, they then challenged the world champion in Go, and this play or this game was then sent out on each television station in China. And yeah, it was a really big deal. And yeah, short spoiler, they beat the champion quite by a lot. So yeah, they basically mastered the game of Go, which experts thought that none of this would be possible within the next 10 years. So again, I will put the link in the YouTube description and also in the Teach Center. And just as a slight note, this guy here in the middle of the picture is actually from Vienna.
That said, I would like to thank you for watching this lecture series. Hopefully we were able to motivate you to get more deeper into computer science and data science, and especially into machine learning and artificial intelligence. At the end, I would also like to wish you good luck for the second assignment and also the upcoming online exam next year. And if we won't see us in one of the upcoming in-person sessions or question hours, I would also like to wish you Merry Christmas, although it's a little bit early, and also Guten Rutsch ins neue Jahr. Thanks again, and see you in one of the upcoming in-person sessions.